Okay. So the next thing, right, these are our energy eigenstates, and because they're the eigenfunctions of Hermitian operators, I'm going to erase this work here, hopefully you have it down. Because they're the eigenfunctions of Hermitian operators, we know that they have to be orthogonal, right? And so let's plug in, let's do the inner product, right? We do the inner product of psi m and psi n, right? And we want to make sure that when we do this inner product, we get delta mn, where it's the Kronecker delta. And I'm not going to do the integral, right? A lot of these integrals you can do, and if you want to do them and get some practice, that's awesome. I have them pre-calculated, so I will just let you know what the answer is, but I just want to show you sort of what the process is. So if we do that, well, this inner product, it's the integral over all possible values of x, right? So that's between 0 and a, of psi m star, but this is they're all real, right? So this is root 2 over a, right? We don't need to take a complex conjugate. Sine of m pi over a x, then times psi n, which is root 2 over a, and if you're evaluating this integral, you could combine these, multiply them together, right? So this is times root 2 over a sine n pi over a x dx, right? And when you do this, indeed, right, if you plug in for different values of m and n, as long as they're integers, right, you get an interesting result, where these functions, it turns out, if you plug in this integral, are orthogonal. This integral is equal to 0, right? This integral is equal to 0 as long as m and n are not equal. And of course, we made sure with normalization, if they are equal, that's just the function squared, right? It's norm squared, but squared because it's real. And we already made sure that that was equal to 1. That's where we got the 2 over a. So it does turn out that it is true that this is equal to delta mn, right? And that is good. That shows that we have orthogonal solutions. Okay. The next thing to do, right, is, well, we have the solution to the time-independent equation. We have psi e, where we have psi n, the little psi n, and now I want capital psi n, right? And we can do that. Capital psi n, we know, is equal to little psi n, so I'll write root 2, actually, yeah, root 2 over a, sine of n pi over a x. Then we have the time part, e to the minus I omega t, or we would write I e t over h bar, right? If we want to figure out, right, just divide this by h bar, we can figure out what omega is, right? Omega n is n squared pi squared h bar, right? Not h bar squared because we divided by h bar, over 2ma squared, right? So plug that into our formula. We have e to the minus I omega t. So I n squared pi squared h bar. So n squared pi squared h bar. And then we'll have a t over 2ma squared. Right? So this is our complex exponential. And that is our solution to the time-dependent Schrodinger equation. Now, here's the interesting part. And I kind of hinted at this in another video, where if we take the norm squared, if we want the probability density of x and time, right? Because this is a function of x and t. So our probability density could be a function of both position and time, but it turns out when we take the norm squared of this, right, where this is the norm squared of psi n, when we take the norm squared, right? We can just, the norm squared of a product is the product of the norm squared. That's sort of a property, and you can show that with the complex conjugates. We take the square of this, right, times the norm squared of this, but the norm squared of a complex exponential is 1, right? So it turns out this thing goes away when we take the norm squared, right? And that's another reason you should be reviewing these complex exponential videos. So we are left with, or not a square root anymore, just the square of this, 2 over a, the sine n pi over a x. And then there's, sorry, this is sine squared. Notice, right, sine squared is sine quantity squared. That's just shorthand of writing it. Notice that the probability density for this state, for the energy eigenfunction, right, this is for the energy eigenfunction, is not a function of time. It is independent of time. And in fact, that is a general rule, right, because this is the form, right, you have psi n, or psi of x times e to the minus I omega t. When you take the norm squared of an energy eigenfunction, right, even when it has time in it, the wave function depends on time. The probability density does not. And that may be a little bit weird to think about, but I'll show you actually pretty soon in a simulation. I will show you how to make sense of that. But we then call energy eigenstates, we call them stationary states, right? And we call them stationary states not because the wave function doesn't depend on time, but because the probability density and the probability of where you find that particle does not depend on time. Only for stationary states, only for states with a definite energy. So I will sometimes use the term stationary state to talk about wave functions with a definite energy, to talk about energy eigenstates. Okay, so the next thing is things you can do with this, right? Of course, you can use our formulas for expectation values to find the expectation value of position, of momentum, of position squared, momentum squared. You can find uncertainty, right? Verify the uncertainty principle, which we'll look at in the next video. Right, and so we can find these expectation values, and I'll do a little bit of that now with I know this video is getting a little bit long. I've got a little bit more to do, but feel free to take a break, of course. I have a little bit more to do before I show you the simulation with a superposition. Right, and this will be the last thing I do before we get to the simulation. So I'm going to erase this, hopefully you have it down. I'm not going to erase our solutions here. Okay. So, now I'm going to use an example of a superposition, right? Where our superposition, I'm going to have psi, this capital psi of x, capital psi of x and t, sorry, be some constant a, which we'll figure out, right? It's part of the generic letter we use for normalization constants. A times psi 1 plus psi 2. Right? And so this is our superposition of the first two energy states. Right? And we know, because these states are orthogonal, right? If we're integrating with x, the t parts won't matter when we multiply, because they're orthogonal. And we showed, right? This is right, if we write it as a psi 1 plus a psi 2, right? We know that the sum of these coefficients norm squared have to be 1. So we know that a norm squared has to equal 1, or sorry, a norm squared plus a norm squared has to equal 1, right? This plus that, right? Those are the probability, right? And remember, this is the probability of having an energy 1, probability of having energy 2, right? And this, of course, if you, right, this is 2a squared. So if you do that, a is 1 over root 2, right? Which makes sense, because then if you take the square of that, it's 1/2. What's the probability, right? If there's no different coefficients, this wave function means you have a 1/2 probability of having energy 1, right, which you can get from plugging in n here, and a 1/2 probability of getting energy 2, right? And so this is our normalization constant, so we can actually rewrite it, right, as long as we've already normalized psi1 and psi2, which we have, right? We've normalized the capital size because we normalized the lowercase, as long as, right, for the energy eigenfunctions. Just want to make sure you remember that condition applies with energy eigenfunctions. So this is 1 over root 2, right? So I'm going to get rid of this work now, right? So we've now normalized it, and we can do a lot of cool things with this, right? We can look at the probability density. And I'm not going to show all the steps just because this video has been long enough, but if you take the norm squared, right, notice it's not just going to be the probability density with the first wave function plus the probability density with the second wave function, because we've got to distribute. And it turns out we're actually going to get a interference term, right? That's sort of where this whole wave-particle duality fits in. Right? We'll have some kind of interference term where we'll have a psi1, psi2 term. And if we expand these out into you know, this being psi1 e to the psi1 e to the minus I omega 1t, right? And this is psi2 e to the minus I omega 2t, right? We will end up getting a very interesting result, right? So if we do take sine norm squared, right? Remember, these are they're stationary states only if they're like the psi1, psi2. If it's a superposition, the probability density could depend on time, and indeed it does, and we get a very interesting result. And this will use a little bit of math using the fact that we know cosine of omega t, right? Cosine of omega t we know is e to the I omega t plus e to the minus I omega t over 2, right? Which we can get if you look at Euler's formula, e to the I omega t being cosine of omega t plus I sine of omega t, and this being e to the minus I omega t cosine omega t minus I sine omega t. If you do that, you can show this result. I may have mentioned that in the video, I think on differential equations I talked about that. But using that result, that's just so you see where cosine comes in, because there's no cosines anywhere. We get the interesting result that I'm not going to show it here, that this is equal to 1/2 psi1 squared, where, you know, it's this. I'm not going to write it all out because I'll show you what I'm interested in. Psi2 squared plus, now this is going to be the interesting part, 2 psi1 psi2 cosine of omega 2 minus omega 1 t, which you can actually calculate this out. This will end up being 3 times omega 1, right? Because if you plug in with the n squared, omega 2 will be 4 times omega 1. So if you just do that, right? But the probability density, and if you go ahead and calculate like the expectation value of position, or if you calculate the expectation value of position, it will turn out that it oscillates in time, right, with the frequency of omega 2 minus omega 1, and I'll show you that in the simulation. 2 last quick things with this example. You know, you can calculate the expectation value of momentum, expectation value of position, and they will both actually oscillate in time. And hopefully you remember how to calculate expectation values, right? Expectation value of x, or really of anything q in this case, or yeah, that's the variable q, or the observable q, is the integral from 0 to a, right? Because that's all we're integrating over here, of psi, right, q hat, sorry, psi star, q hat psi, where these stars will actually matter, right? dx, right? And note, when you do this, when you expand this out, we have to remember it's a norm squared, so you take the complex conjugate, right? Because these are complex, right? It's just the part in x that is not complex, right? And if we do this for position, we do this for momentum, we'll get some interesting results. We can also do this with energy, right? But there's actually a little bit of an easier way that we can do this with energy, and hopefully you can show why this is equivalent to the integral way. But I just want to make sure you remember the expectation value of energy, right, would be the sum, right, over all values of n of the probability of that energy, right, times the energy, right? So the probability of E sub n times E sub n. That's how we calculate averages, right? But if we just do this, well, this is, right, 1/2 E1 plus 1/2 E2, right? And so instead of going through all the thing with the operators, right, we can calculate averages that way as well. Right now, this is sort of just quick pointers as to all the different cool things we can do with the solution, right? And you can of course show that. It's a lot easier to show it if you just use, finding the expectation value of, say, the Hamiltonian operator, right? Which will also be the expectation value of energy, right? We know that, if you plug this in, you'll get, when you act on this wave function, you'll get, with the Hamiltonian, you'll get 1 over root 2 times E1 psi 1, because it's an eigenstate, plus E2 psi 2, right? And then do the inner product, use the fact that psi 1 and psi 2 are orthogonal, and you'll end up getting, with this result, just taking a much longer path, right? Okay, so I know that's been long. Thank you guys for watching this whole thing. And now, as promised, we get to the simulation. So I'm using a PhET simulation, link in the description. And here I have, I've set up, in fact, I couldn't get the infinite square well. PhET doesn't do that one. So I've set up the finite square well, right? Which we'll learn how to solve that in a little bit. But as you can see, the energy difference is pretty significant. So it's sort of like it's an infinite square well, until maybe we get up to here, then you start seeing the differences, right? But now this is the probability density here, right? Or sorry, this is the wave function. This is the magnitude of the wave function. But if I were to show you the real and imaginary parts, I want to show you what happens as time goes on. As you can see in this demonstration, the wave function, the real and imaginary parts, the wave function depends on time. But what doesn't is the magnitude, right? The norm squared of the wave function. Or this is really just the norm of the wave function, not squared. That does not depend on time, and nor does then the square of that white graph, the probability density, does not depend on time either. Right? And we can show that. This is just an interesting thing to look at. I'm actually going to freeze this. I'm going to go to, let's look just at the real part here. Okay. This is also a graph of the eigenfunctions, right? Instead of graphing them, I'd figure I'd let this one, right? The first state has just one bump. The second state, slightly higher energy, has two bumps. Third one has 3. One has 4, right? And I just wanted to show you that. Again, you can play around with this demonstration too. I'll have the link in the description to look at all of the different states. The last thing I can do here is do a superposition. We'll actually do the thing with psi 1 and psi 2 that we had. So now we can know that psi 1 and psi 2 are, right, they have that 1 over root 2 coefficient. But on this, right, even if we don't know exactly what 1 over root 2 is, right, and how to type it in here, I'll just make it 50-50. And it will normalize it for us. 0.71 is 1 over root 2, approximately 1 over root 2. And now, I'll show you the real part, the imaginary part, the magnitude. We let time go on here. And as you can see with this magnitude, it's actually going to oscillate back and forth, and you can see it better with the probability density. Right? Here, the particle is most likely to be here, and it oscillates back and forth. So it's no longer in a stationary state because we put it in a superposition state where 0.71 is again 1 over root 2. So it's normalized. Okay, so that is this video. Feel free, of course, to play around with this demonstration, with this simulation. And thank you again. I know it's been a long video, but I will see you in the next video where we do a little bit more with these solutions to the for the particle in a box.